Good day, my scholars. This is my school channel and my name is Abiola. For this video lesson, you'll be joining me to solve the JAMB CBT past question for the subject Physics, the year 2008. Do not go anywhere, stay with us and we'll be right back. You're welcome to my school YouTube channel. Right there, you'll be joining me to tackle questions 1 to 25. So do not go anywhere. Stay with me as we begin with question 1. Which of the above are the correct SI units of the quantities indicated? All right, we know first mass times acceleration. We have torque right here. That is actually the rotational effect of force. We have current and we have power. Okay, so this is the unit for force, Newton, right? This is the unit for torque, that is Newton meter. This is very correct as well. Current is measured in amperes, all right? Then power in watts. So, which of the above, okay, with the correct units? Yes, all the quantities you can see here, their respective units are properly attached. So, option D is the correct option. 2. Which of the following is not a vector quantity? So we have scalar quantity and vector quantity, or scalar quantities and vector quantities. Okay, vector quantities, you know, there is a magnitude or numerical value and direction. Very important. So examples of vector quantities, we have acceleration, displacement, weight, force, etc. All right, so the exception here is altitude. So option A is the correct option. Question 3. If a wheel 1.2 meter in diameter rotates at 1 revolution per second, calculate the velocity of the wheel. All right, very easy. So recall that angular velocity, right, equals the angle over time taken. Or if you carry out your expression, you can still get this, 2 pi f. All right, so right here we are solving for, or we should be solving for linear velocity. So remember, linear velocity is actually the product of radius times this. And we recall that this is 2 pi f. So that will be radius times 2 pi f. All right, so f represents or stands for frequency. And we can see that 1 Hertz, Hertz is the unit for frequency. So 1 Hertz equals 1 revolution per second or 60 revolution per minute. You see that right now. So the question says rotate at 1 revolution per second. So we have this. Remember that the radius we are given diameter instead of radius. And you remember that diameter equals radius divided by 2, right? Diameter equals to 2 times of radius. So to get radius, what do? We divide both sides by 2. So radius is actually diameter split into 2. All right, split into 2. So diameter we are given from the question is 1.2. So R equals 1.2 divided by 2. That should give me 0.6. So let me fix in the value. So we have radius as 0.6 times 2, right, times the pi, which is 22 over 7. Do we say that? Times frequency, which is 1. All right, so if we carry out the multiplication here, what we should have, because we are looking at linear velocity, so your unit should still be provided in meter per second. All right, so if you carry out this solution, 0.6 times 2 times this, you should have something around 3 point, I think maybe 77 or 76 thereabout. So I can just bring my solution to 3.77, all right, meter per second. Or some expression will give you something like this, 3.77 meter raised to power minus 1. Okay, this thing means 1 over s, meter times 1 over s, still gives you the same thing. So let's go back to the screen to select the right option. Of course, we have a confirmation right here. So option B is the correct option. Number 4. Which of the above conditions must hold for a body acted upon by a system of 3 coplanar forces equilibrium? Okay, so take note of this. We can have parallel coplanar forces or non-parallel coplanar forces. So right there are no specifications. So we can work with generalization. So that means we are combining conditions for both parallel and non-parallel, and all 3 satisfy. Okay, so you can see all the 3 forces must be concurrent. That's very correct, even under non-parallel. Okay, the upward force is equal to the downward force. Of course, we are talking about algebraic sum, right? So right here, this accounts also for parallel. Okay, so the algebraic sum of the moments about any point must be 0. What this implies is that the sum of clockwise, right, total clockwise, and it should be equal to sum of total anti-clockwise. All right, so sum of anti-clockwise, total sum, they mean the same thing. So do you get that now? So anti-clockwise equals to clockwise. All right, upward and downward, then the same. So all these 3 conditions, they can be found in both parallel and non-parallel coplanar forces. So there are no specifications. So I can work with this generalization. So I can pick statements 1, 2, and 3. So option D is good to go. 5. What is the frequency of vibration if the balance wheel of a wristwatch makes 90 revolutions in 25 seconds? So remember, frequency is actually revolutions per second, revolutions or circles per second. So very easy. So frequency, I have revolutions, right? Or circles, which is revolutions, we have 90 per second. How many seconds do we have there? 25. So for this experience, let's see how much circle is made, right, per second. So let's divide. I have 5 here, 5 here, that should be 18, yes. Then I have 18 divided by 5. Yes, I know 5 can go in 18, that should be 3 times, right? Remaining 3. 3 over 5 is actually 0.6. Okay, if you recall the way we work around mathematics, no, we have 3 number, 3 over 5. Right, so if I want to do this, of course you can punch your calculator. This is just to give us a kind of refreshing. Okay, I have 5 outside 3. 5 in 3, that is impossible, so put 0. 5 in 30, that is 6. 5 times 6, 30. 30 minus 30, that's 0, 0. So that's definitely 0.6. That is 3.6. Remember, the unit for frequency is actually hertz. So you don't need to do this. Okay, just punch your calculator. 90 divided by 25 is going to give you this 3.6. So let's go back to the screen to secure 3.6 hours. Okay, we have 3.60. Okay, so option D is the right option. 6. If a body mass 5 kg is thrown vertically upwards with velocity u, at what height will the potential energy equal to the kinetic energy? So let's just do it together. Remember, we said when is P equals to KE. So let's just pull out their formulas, isn't it? So this is mgh, then this is half mv squared. Remember, we had to use u from the question. All right, so I'm just trying to relate. I can give an explanation why we are using the u instead of v, but let's just take what the question has said with velocity u. Okay, so dividing both sides by m, this is gone. So I have gh equals half u squared, right? That is u times 1 is still the same thing. So basically I can have this u squared over 2. Okay, so we are asked to make h the subject, so I can divide both sides by 1 over g, or by g, isn't it? Times 1 over g. Okay, so I have my h equals u squared, right, times 1, that is u squared, over 2 times g, that is 2g. So you know that at the maximum height, it is all potential energy, right? Okay, so KE right here is 0, PE is maximum. Right here, PE is 0, right, Ke is maximum. So because right here, you're talking about potential energy due to the level or position of a particular object. So you will realize that midway, right, half of this height, that is when this will be equals to this. Okay, so half of this will be u2 times 1 over 2, isn't it? That is u squared times 1, I have u squared over 2 times 2, I have 4g. So half that height is where PE equals KE. So let's go back to the screen to select this value. So we have u squared over 4g presented in option B. So option B should be your option. 7. Counting of currency notes with moist fingers is based on the principles of what? This is actually very funny though. So if you look at diffusion, you're talking about movement of molecules from region of higher concentration to region of lower concentration. Okay, cohesion, you're talking about that attraction, force of attraction between molecules of the same, you're talking about the same substance, right? For instance, the cohesion, you notice when you pick mercury, for instance, mercury will not wet a glass compared to water. So that's why you will notice that the adhesion, that is the force of attraction between molecules of different substances like water and glass. So you see that water will wet the glass, but mercury will not, because force of cohesion here is greater than adhesion for mercury. All right, so we're talking about different molecules here. We will look at currency notes and moist finger, wetness. Okay, so two different molecules entirely. Viscosity. So viscosity, we are talking about the internal friction, all right, between layers of probably liquid or gas that are moving or in motion. Okay, so like you can say the viscosity of palm oil, you can compare to that of water. Which one flows out faster? Okay, so the correct option is actually adhesion with different substances entirely, force of attraction. So option C is the right option. 8. A motorcycle of mass 100 kg moves around in a circle of radius 10 meters with a velocity of 5 meters per second. Okay, so find the coefficient of friction between the road and the tires. Okay, so at first we have to use the concept of centripetal force. You're talking about that inward force required to keep an object moving in circular paths, right, with constant speed. So all of those grammars, so we should just have this, right, mv squared over r, where this is also measured in meters. Take note. So I have the mass is actually 100 times v, which is also meter per second, so that's the unit 5. So 5 square, that is 5 square, right, or 5 times 5 over radius, that is 10. So 10 here 1, 10 here 10, right? So I have 5 times 5, 25, times 10, that is actually 250. Okay, all right, so let's come to the normal reaction. Remember, the formula there is actually normal reaction is actually mass times gravity. Okay, in case when angles are involved, then you can say maybe cos theta or thereabout. So mass is actually 100 times gravity, that is 10. So I have 1000 newtons. So coefficients of friction, all right, is actually the frictional force, right? Frictional force over the normal reaction. Frictional force over normal reaction. So it is simply this over the normal, which is 1000. So 250 here 1, 250 here 4. So that is basically 0.25. Okay, so 0.25. Let's go back to the screen to select 0.25. Yes, we have it right here. So option D should be your choice. Number 9. A spring of force constant 500 Newton per meter is compressed such that its length shortens by 5 centimeters. Okay, so the energy stored in the spring is what? Okay, very easy. Energy stored in a spring has this formula half Fe, okay, where F is actually Ke. This is based on Hooke's law, right? So that implies half, right, Ke times this E here, that will be half, right, Ke times E, Ke squared. So we see the derivation now. Okay, I believe some of us know this very well. So let's work. So we have half times K, that is the constant, that is 500 times E, right? The compression of the extension, which is 5 centimeter. Now it's supposed to be in meters. So if you are converting 5 centimeter to meters, so at first we have to do that. Okay, let's just carve out somewhere here. So we know that 100 centimeter equals 1 meter, right? So 5 centimeter equals X. So when we cross multiply, we have X times 100 equals 5 times 1. So dividing both sides by 100, so basically I should have X equals to 5 over 100, okay? Or 0.05, if you want to put it that way. So let me just work with 5 over 100. Remember, raised to power 2. So instead of me rewriting this, I will just wipe this off. Then I have times 5 over 100. Okay, so 100 year 1, 100 year 5. 5 year 1, 5 year 20, 5 year 1, 5 year 4. So 5 times 1 times 1, I have 5 over 2 times 4. That is 8. 5 divided by 8, that should give me 0.625. Remember the units, joules. So this should be your answer, 0.625. Let's go back to the screen together. Okay, so we have a confirmation right here. So option A is the right option. Do not forget to utilize any of the Myschool tools. All you just need to do is to first click on the link in the description below. This is going to get you to the Myschool website. Right there, you get to download the Myschool mobile app for your Android devices, or you can check out Myschool software for your laptops and computers. So join me as for question 10. In the air's apparatus, okay, water rises to a height of 26.5 centimeter in one lane. All right, so if a liquid rises to a height of 20.4 centimeter in the other lane, what is the relative density of the liquid? So if you want to sort out relative density of the liquid, you can use the YouTube, normal U, letter U, YouTube, and the air's apparatus. Okay, so right there it's very easy. Just take the value of this divided by this. So that is 26.5 divided by 20.4. It should give you something around, I think, 1.2990 to thereabout. So if you estimate, all right, or approximate, you should have 1.3. So option D is the right option. Please do not forget to always hit that like button. Also use the subscribe button and always tap on bell notification for you to get alert immediately we upload the next video content. Question 11. When cold water is poured on a can containing hot water, the can collapses because, all right, so at first if you get, the can be aluminum can, aluminum soda can, or kerosene can. All right, so once you pour water into it and you heat, all right, the container, heat up the container, all right, what happens is that you are transferring, of course, heat energy, you know, to the water molecules. You know, those molecules gain enough energy and they begin to move faster. You know, before you know, they begin to escape as steam. All right, so in conversion, in such phase or such phases, you know, what you are going to notice is that air will be pushed out of this container, isn't it? Out of this can, to be precise. Then the steam will then fill up the entire space, you know, in that particular can. So once this happens, then you can notice the action right there. So at this point now, if you are now pouring cold water on the can, all right, so pouring cold water means you are decreasing the temperature and you are decreasing the kinetic energy and you are decreasing the collision between the particles of the steam, right, and the walls of the container. You know, when the gas molecules collide with the wall of the container, what you notice or what you will have is gas pressure. All right, so once you are pouring cold water, you have reduced temperature, hence kinetic energy will decrease, and number of collision with the wall of the container will decrease. That means you have decreased the gas pressure. So having decreased gas pressure, what will you notice? You will notice that the internal pressure in the container, of course, you realize it's sealed now after you have let air escape. The internal pressure in the container has dropped compared to the external atmospheric pressure, and that is where the crushing comes in. Now, definitely, you know, the atmosphere contains lots of air. And you know, air, exactly, it has weight, isn't it? So we do not feel this weight or this pressure, okay, because our internal system is able to balance with the external pressure outside. So let's come back to this question. So when cold water is poured on a can containing hot water, it's going to cool off. So cooling off means you have reduced the alkylation power. So the can will collapse, right? Why? Because the external pressure becomes greater than the pressure within the can. So option D is the correct option. 12. An empty density bottle weighs 2 Newton. If it weighs 5 Newton when filled with water and 4 Newton when filled with olive oil, the relative density of olive oil is what? So when you are trying to work around relative density, specific gravity, you are talking about the ratio of the density of a substance in reference to a particular substance. So right here we are looking at the ratio of the density of olive oil to water. Water is the reference now. Okay, so we have it this way. Very easy. So typically, when it was filled with olive oil, it weighs 4 Newton, right? Minus when the bottle, density bottle, was empty, and that is 2. Then when we filled it with water, it weighed 5 minus, okay, when empty. So I have 4 minus 2, that is 2 over 5 minus 2, that is of course 3. So we have 2 over 3. Let's go back to the screen. Select 2 over 3. So option B is the right option. Number 13. The thermometric properties of a thermocouple is the change in what? Okay, thermocouple, we are looking at electric thermometer. Okay, thermometer. All right, so basically let's bring together this principle. For the operation of this kind of setup for thermocouple. All right, so you're looking at 2 different metals, right? Probably copper and constantine, or copper and iron, or iron and constantine. All right, so the logic there is just for you to set up, these metals in such a way that they're going to form a complete circuit, right? So one end, or one junction, if you want to use one junction is hot, the other is cold. So right there you now see current will flow. All right, so you should just notice is that this occurs because of the temperature difference. All right, so the greater the temperature difference, then you're talking about the greater the EMF that will be produced. All right, so some presentation will tell you electric potential difference. Okay, very well. So EMF, potential difference, the flow of current, these are things that should occur in this kind of setup. So the correct option here is for a thermometric thermometer. So that should be option B, electromotive force. Question 14. During summer, okay, so the balance wheel of a clock expands. Okay, so what effect does this have on the accuracy of the clock? All right, so if you look at advantages and disadvantages of thermal expansion, right? So, disadvantages, probably when you pour hot water into a glass, the glass will crack. Okay, and also, expansion of railway lines, that's why they have to allow for that expansion and contraction as well. Also it affects the balance wheel of a clock or even wristwatch. All right, so let's come back to this. So what has happened, when during summer you are talking about intensity of sunlight, right? Both the length of exposure or the concentration, to put it that way. Okay, so that's more like a chemistry term. So, we're having enough. So that means the experience of heat, and when there's heat, there's expansion. All right, so if expansion occurs, imagine this. Let's just do it together. Imagine that when your clock ticks, right, the hand ticks, from year to year makes 60 seconds. But once you apply heat, there's going to be an extension in the length of this. So that is, if year to year supposed to take 60 seconds, that means you have 60 seconds plus some kind of microseconds, right? So that means the time is going to take the clock to actually complete a particular period will increase. So if that time increases, that means you are losing time. So because before it's going to reach 60, it's going to take a longer time. So what effect does this have on the accuracy of the clock? So the clock will lose time. All right, so the normal thing that it covers within a specific time is going to take longer to do that. So that means before it can count that particular 60 for you, time has been lost. Okay, so I don't know if that explanation really helps. but that's how I feel like I can relate it to us. So the effect of this expansion is that the clock loses time because of an increase in length, simply to put. So option C is the correct option. Number 15. A sealed flask contains 600 cm cube of air at 27 degrees Celsius and is heated to 35 degrees Celsius at constant pressure. Okay, so the new volume is what? So just take it off. This is actually Charles' law. You know, basically Charles' law is just saying that when you heat up a gas, right, its volume, it expands, right, its volume increases. So that its volume is proportional to temperature. Okay, so let's do this together. So recall for Charles' law, you know, V1 over T1 equals V2 over T2. Recall that your temperature should be in Kelvin. So the first temperature we are given 27, right? If you want to convert to Kelvin, you have to 273, and that should give us 300 Kelvin. All right. So the second temperature we are given, I think 35. If I'm not, is it 35 or 30? Yeah, 35. Okay, plus 273. I think that should give me 308, right? 308 Kelvin. So the first volume is 600. So let's just plot in this value. So we are looking for V2, isn't it? So let's cross multiply. So I have V1 T2 equals V2 T1, dividing both sides by T1. So basically V2 equals V1, which is 600, times T2, which is 308, over T1, which is 300. So 0 cancels 0, 0 cancels 0, 3 here 1, 3 here 2. So 2 times this, it should give us 616. Remember the unit of volume that we've been using? Centimeter cube. So 616. So let's go back to the screen to select 616 from the options. Right. So option D is the right option. 16. A block of aluminium is heated electrically by a 25-watt heater. If the temperature rises by 10 degrees Celsius in 5 minutes. Okay, so the heat capacity of the aluminium is what? So we are looking at the heat energy involved, we are looking at the heat capacity and the likes. Okay, so recall this, that quantity of heat actually equals this times this, isn't it? Alright, and you can also use this formula. Remember that this Q is also equals to MC delta theta, right? Where your heat capacity is different from specific heat capacity, where this big C, which is heat capacity, this is small c, specific heat capacity is actually equals to MC. So if I want to rewrite this, I can write this as big C, right, replaced by this, isn't it? Delta theta equals Q, right? Isn't it? And we know that Q is also equals to PT. So that implies equals to PT. So we have to find its capacity. So what do? I divide both sides by change in temperature. That is delta theta. So I have my big C, its capacity. Wow, that's super big. Equals PT over this. Okay, so what is the power of the heater? That's 25 watts times the time. That's actually 5 minutes, but we have to convert to seconds, right? Yeah, 5 minutes. So that will be 5 minutes times 5 times 60, isn't it? Over the change in time. You can say it there. Change in temperature. The temperature rises by 10 degrees Celsius. So I have 10, right? 10 here 1, 10 here 6. Okay? This is 6 times 5. That is 30. So 30 times 25, that should give me 750. Okay, 750 joules per Kelvin. Or you can see some expression like this. You see the same thing, raised to power minus 1. You see the same thing. Right, so let's go back to the screen. 750. Okay, so option B is the option. Question number 17. If the partial pressure of water vapor at 27 degrees Celsius is 18 millimeter mercury and the saturated vapor pressure of the atmosphere at the same temperature is 24 millimeter mercury, the relative humidity at this temperature is what? So just take it easy because it's super easy. All right, trust me when I say so. So if you're looking at relative humidity, right, it's actually a consideration regarding, you know, the ratio between how much water vapor is present, right, and how much normally saturates certain volume. This is what I mean. Let me say the volume of air that we have, volume, okay, let's say the volume is actually 30, right, cm cube. And from the question right here, I have the temperature is actually 27, okay, temperature is 27 degrees Celsius. Yes, degrees Celsius. So, what relative humidity is about is that, okay, looking at this exact volume and this exact temperature, okay, so how much water vapor is present at this temperature for this particular volume of air? Do you get? Okay, how much is present, right? So from the questionnaire, we are told that we have 80 milliliter mercury, right? Over, normally, how much should saturate this? Or how much should really, do you get what I'm saying? So how much should saturate this? Okay, so how much saturate, that is actually 24. Do we see that now? So relative humidity is just like the ratio of, okay, how much water vapor is present to how much saturated vapor pressure do you really need? Do you get? Or actually that does the magic. Okay, so at this volume, at this temperature, okay, how much do we have? We have 18. How much fills this? How much saturates this? It's actually 24. Do you see? There's just the ratio of that. So that's simple. Okay, so remember this value is just an assumption, just to explain this concept. So let's just make it times 100 since we are working around percentage based on the options supplied. Okay, so I know that what can put through here, of course, I can see 6 right here, 3 right, 6 right here, 4. All right, so I have 4 here, 1. 4 here, 25. So 3 times 25, that's actually 75% humidity. So let's go back to the screen. Let's see if we have 75%. Okay, so yeah. So option C is the right option. Number 18. In a good thermos flask or vacuum flask, okay, we have its loss is reduced through the following features except. So what are the features of a good thermos flask? Okay, so we have the insulating cork, you know, the one that serves as the base support. It actually helps to reduce its loss through conduction. All right, we have the silvered walls. This is to reduce its loss through radiation. All right, then we have the vacuum. That's for reduction of its loss through conduction and convection. Then we have at the top the cork lid, you know, that reduces its loss through convection. All right, so I've mentioned like 4 features, basic features, right? We don't have lens surface. When you're looking at lenses, okay, you are looking at probably camera, you know, your telescope and the likes. So the correct option here is option A, the lens surface. 19. Given the progressive wave equation y equals 5 sine, we have 2000 pi t minus 0.4 x. Okay, so calculate wavelength. All right, so we recall the equation for a progressive wave. We can use this representation. Okay, wavelength is t, then phase angle. And you remember that phase angle too, you can use phase angle as a kx, or phase angle equals kx. All right, so let me just do this. So if you want to make a proper comparison, this is A, this is the sine, right? This, right? Then we have the t here. Then that means k is actually 0.4, isn't it? Then x, this is x. Do we find that interesting? Okay, so, right, where k is actually 2 pi over lambda, and lambda is the wavelength that we are looking for. All right, so that means if we bring this is k, right, and this is x, isn't it? So this is what we should have. So that implies that 2 pi, right, over lambda x equals kx. Isn't it? That's the formula, right? So let's work around that. Okay, so we have where pi is actually 22 over 7 or 3.142. All right, so that will be 2, right, times 3.142, 142 rather, times x, isn't it? Times x over the lambda that we are looking for, right, equals k, that's 0.4, times x. So we know x cancels x. So by the time we cross multiply, I will have lambda coming here, right? So that will be 0.4 times lambda, isn't it? So what would I do? I'll still have to divide both sides by this 0.4 so that I can find my wavelength, isn't it? So that implies that my wavelength will be equals to 2 times 3.142, right, over 0.4. Okay, so by the time I carry out this, I should have 15.71 thereabouts. So roughly I can bring it to 15.7. Remember wavelength, that is measured in meters. So this should be the closest that we should get as our correct solution. So let's go back to the screen. Yes, screen of course, to select the right option. So we have a confirmation, option B. Do not forget that you can ask those questions right now. All you just need to do is to click on the link in the description below. This is going to get you to the Myschool website. Okay, so from there you can ask your questions, you get to interact with our solution providers, you get more exposed and enlightened. All right, so join me as of question 20. The fundamental property of a propagating wave, which depends only on the source and not the medium of propagation, is the what? All right, so this question looks very tricky, right? It's very tricky. All right, and I've seen several contributions and they are worthwhile as well. So we are looking at the fundamental property of a propagating wave. You can just say propagating wave is actually a moving wave. All right, just put it there. Simply. All right, so this depends only on the source, not on the medium. So at first, we have to look at certain properties, right, that certain properties that change when they change medium. All right, so those properties include velocity, wavelength, especially. All right, so you notice that the velocity of sound or speed of sound in air differs from the speed of sound in water, differs from the speed of sound in metals or solids. You see that, right? So this and this will change as medium changes. Okay, so that is settled. So we have two options left. All right, we have B and C. All right, if you look at this closely, harmonics, right? Harmonics are just frequencies, all right, which are multiples of the fundamental frequencies. Or you can say harmonics are whole number multiples, okay, of the fundamental frequency. Fundamental frequency. All right, and fundamental frequency, they are the lowest frequency, but they are also audible. All right, so you can see that everything rises and falls on this frequency. All right, so this is the fundamental property, okay, that just depend on the source, not on the medium of propagation. So I will go for option C, frequency. Do not forget to share your better steps or explanations. You can use the comment section below, right? Indicate the question number and the explanations, views or reviews you would like to share with us. 21. Which of the above is a phenomenon of total solar eclipse? All right, so we are looking at solar, that is eclipse of the sun. All right, so at first, the best consideration should be rectilinear propagation of light. All right, this is an established fact that light travels in a straight line. Okay, so other application of rectilinear propagation of light include shadows, right? Then we have eclipse. So they are like eclipse of the sun, which is solar eclipse, eclipse of the moon, that is lunar eclipse. All right, so eclipse of the sun or solar eclipse, it is when the moon actually comes between the earth and the sun. All right, the source of light. Okay, so this is one phenomenon that you can attach to this concept. Another phenomenon that we can consider is this: relative motion of the earth, sun, and moon. You know, if you take note of this, when the earth now comes between the sun and the moon, what you're going to have is that lunar eclipse. So you can see the relative motion of these bodies actually should account for eclipse. All right. Okay. Then we have, okay, conservation of light energy. Generally we talk about conservation of energy generally, that energy cannot be created nor destroyed, all right, but converted from one form to the other. Basically, you are saying a closed system, all right, the energy there in that system remains constant, except there's an exposure and there's a shift. Okay, so let's come to total internal reflection of light, where the application comes in, your binoculars, mirage, the field view of fishes underwater, so these two are cancelled. All right, so the best is this, right? Then I should also consider this. So I and high V. Where do I have that combo? Okay, so the best thing we can do for this question based on the provision of options should be option D. Question 22. An object of height 4 cm is placed in front of a cuboid pinhole camera of size 6 cm. Now, if the image formed is 2 cm high, how far is the object from the pinhole? So we are looking for object distance. So magnification is actually the ratio of the image height to object height, right? Okay, so if we have this, we can just use this formula, magnification, right? Or you don't even need to write this out. Okay. So remember I said image height, right, over object height. Then you can say the length of the camera, okay, which is the pinhole camera size, okay, or you can say the image distance, right, from that, from the camera, the image distance from the camera over object distance from the pinhole. All right, so whatever thing you want to use. So the value given there is actually 6, all right, over what we are looking for, the object distance, which is x. Okay, so let me substitute the values we have here. So image distance is provided as well. So if the image formed is 2 cm high, so this is 2 cm, object distance should be, object height rather, an object of height 4 cm, so this is 4, right? So if I cross multiply, so that is x times 2 equals 4 times 6. So what can I do? Divide both sides by 2. Right? So 2 times 6, that is 12. So the object distance is actually 12 centimeters. So let's go back to the screen to select the correct option. So we have 12.0 centimeters. So option C is the right option. 23. An object of height 5 centimeters is placed at 20 centimeters from a concave mirror of focal length 10 centimeters. So the image height is what? So take note of this. Okay, so for a concave mirror, you know that your F is always positive, so that is settled. All right, so the image that will be produced, okay, will either be real or virtual, depending on the position of the object, right, from the mirror. Okay, and the image will be real, okay, when object distance is greater than focal length. So if you look at this, it's placed 20 centimeters and focal length is 10 centimeters. So you can see object distance is bigger than focal length. So that means the image produced will be positive. All right, and if that is positive, if it is real, that implies that your image and your object will be what? Positive. We get that now. So that means the formula we are using is going to be 1 over F equals 1 over U plus 1 over V. All right, so let's make that happen for ourselves. So at first we want to find the image distance. So remember, we have this. You can say 1 over U plus 1 over V, whichever one works for you. So I have to bring this here so that I can find this. So that should be 1 over F minus 1 over U equals 1 over V. Okay, so 1 over F, that's actually 1 over 10, right? Minus object distance, that is 20, equals 1 over V. Okay, so their LCM is actually 20, right? 10 in 20, that is 2. 2 times 1, that is actually 2. Right, minus 20 in 20, that is 1, times 1, that is 1, equals 1 over V. And that is 2 minus 1, that is 1 over 20, equals 1 over V. So we cross multiply, of course. So that should be, okay, so I should have V times 1, that is actually V, equals 20 times 1, that is actually 20. Remember the units if you want to put it there. Okay, so I have this presentation already. Okay, so let's move to the next step. So we are asked to find image height. Okay, so we are just going to introduce a magnification formula. So remember that image height, right, over object height equals image distance, right, over object distance. Okay, so we're asked to make this the subject of the formula. So that means image height, okay, equals, that will be this times this over this. Okay, so let's slot in the values. So we have image height equals the object height, which is actually, we're giving object height as 5 times the image distance, which we have gotten as 20, over the object distance, which is as well 20. So 20 strikes 20, so we are left with 5. So the image height should be gotten as 5 centimeters. So let's run a confirmation from the screen. Okay, so where do we have that value? Okay, it's placed with option D. So option D is the right option. Question 24. Convex mirrors are used as driving mirrors because images formed, all right, either you refer to convex mirror or diverging mirrors. Okay, they are always erect, diminished, and virtual. Okay, then coming to sign convection, you know their focal length is negative. All right, that's just extra information. So the correct option here is the option A, erect, virtual, diminished, or erect, diminished, virtual. So option A is good to go. Number 25. An object placed at the bottom of a well full of clear water appears closer to the surface due to the concept of refraction. So right there you can pull out some real depth and apparent depth. Okay, so the water tends to appear shallower. Okay, so then now let's come to diffraction. The correct option, of course, is C for refraction. You know, diffraction probably, you know, a wave is trying to just maneuver itself through a blocked path or through a barrier, around the barrier to put. Okay, then we have reflection. You know, reflection is probably the concept between you and your mirror. You know, incident ray from your face then strikes the mirror. Then what you are seeing is the reflected ray. All right, so then we have polarization. Polarization is actually from the word polarization, you can attribute to the Latin word polos, which means axis or direction. So the correct option, once again, is option C for refraction. So we've come to the end of this video segment, but you know that there are more segments to come. What you just need to do is to always hit that like button for us, and do not forget the subscription button, and always tap on bell notification for you to get alerts immediately we upload the next video lesson just for you.